Hi everyone, Dr. Burns here with our next lesson in our acid-base chapter. Today we're going to be talking about the concept of things being acidic and basic and being able to quantify that through pH and pOH. So in our previous lesson we talked about how the equilibrium constant for water, K sub W, is equal to the product of the hydronium ion concentration and the hydroxide ion concentration, and that since it's an equilibrium constant, there is a value that is given for it at 25 degrees Celsius. So since this product of those concentrations is equal to a constant value, the relative amount of each obeys a fixed relationship, as we saw in our previous lessons. So depending on which ion concentration is in excess, the solution will either be considered acidic or basic. So when they're equal to each other, when the hydronium and the hydroxide ion concentrations are equal, then the solution is said to be neutral. If we have a higher concentration of hydronium over hydroxide ions, then that solution is acidic. Now, if you remember from our previous lesson, we said that if there's hydronium ion concentration or hydronium ions in the solution as one of our products, then we've done a reaction with an acid. So this is another way to remember that. Higher H3O plus, higher hydronium concentration suggests acidic. When we have a higher hydroxide ion concentration compared to the hydronium ion concentration, then that solution is considered basic, which also falls in line with what we discussed in our previous lessons, where if we see hydroxide ion as a product of a reaction, then we did a reaction with a base. So when we say COH minus, we should think basic. So if the OH minus concentration is higher, then it's going to be more basic. The acidity of an aqueous solution depends only on the concentration of those hydronium ions, so at the H3O plus concentration, because H3O plus means acidity. So we can quantify how acidic something is via the pH. So the pH of a solution is defined as the negative base 10 logarithm of the hydronium ion concentration, as long as that concentration is in units of moles per liter, which is our typical concentration unit, moles over liters. So we can define that through two different equations. If we want to find the pH of a solution, we take the negative log of the H3O plus concentration. So if we know the H3O plus concentration, we can find the pH. If we know the pH of a solution and we want to find the H3O plus concentration, then all we have to do is do 10 raised to the negative pH value. Now I want to make a note about the phrase, the wording of pH. So the P stands for base 10 log. We're going to see that often if we see a P and then something else after it. That's usually meaning base 10 log. So we do it the logarithm of some number. The H stands for the H plus. Now H plus, as we'll see, and H3O plus are interchangeable, because if we just take one water and break it down, we get H plus and OH minus, which is typically what happens in a acid-base reaction. However, if we're reacting with another water, that's when we get the H3O plus. So we'll see that H3O plus and H plus are interchangeable. They're equal to each other. One just has some additional hydrogens and oxygens to account for an extra water that may be in the reactant. So the H of pH is actually referring to the H plus slash H3O plus concentration specifically. So in pure water at 25 degrees Celsius, we determined that the H3O plus concentration is 1 times 10 to the minus 7. Okay, we took the square root of the kW and we found that it was 1.0 times 10 to the minus 7. So if we wanted to find the pH, this should not have a log in it. There we go. Get rid of that log in there. There we go. So the H3O plus concentration is just equal to 1 times 10 to the minus 7 molar. There we go. So if we wanted to find the pH, we would take the negative log of 1 times 10 to the minus 7 and get that the pH of pure water is 7, which you may know already. You may have heard of that before from previous courses. That's not common knowledge to everyone, but some people already know that just from life in general. So the pH of water is 7. 7 is indicative of something that is neutral, because we know that in pure water, the concentration of H3O plus is equal to the concentration of OH minus, which we said in our previous slide that is a neutral solution. So pure water at 25 degrees Celsius is going to be considered neutral because it has a pH of 7. Now when we're discussing pH, and we're going to move on to pOH as well, this is always going to be a dimensionless quantity, so it has no units. There are no units in pH. It's just a number, and that's it. So let's practice using these two equations. So we want to determine the pH of each solution with the given hydronium ion concentrations. So we know this, we know H3O plus, and we want to find the pH. So all we have to do is say that the pH is equal to the negative log of whatever that concentration is, 5.3 times 10 to the minus 4. And then we just have to plug that into our calculators to solve for pH. So let's grab our calculators and solve this problem together. So we are going to do the negative log of 5.3 times 10 to the minus 4. And we get a pH that is 3.3. We'll go with 2 sig figs from our original number, 3.3. So our pH is 3.3. We can do the same thing for the next one. So negative log of that concentration. We do negative log 7.1 times 10 to the minus 6. And we get 5.1 as our pH. So now pause your video and try the last one yourself on your own calculator. So what we'll do is we'll just plug that number in, negative log of 4.8 times 10 to the minus 12. So negative log of 4.8 times 10 to the minus 12. And we get a pH of 11. Okay. For our next set of practice, we want to determine the hydronium ion concentration for each solution given their pH values below. So we have 4 pH values and we want to find the H3O plus concentration. So we are going to use this equation here where we want to find the concentration but we're given the pH. So what we're going to do is we are going to take those pHs and we are just going to do 10 raised to the negative of that pH value. That negative in the exponent is very important. Now some calculators have their 10 to the in different spots. I personally like to use the second log button because it automatically does a 10 raised to that. You could type it in as well. Either works. They're both going to do the same math. So, but I personally use it because I just remember that it's the opposite of a log, and that's where it is. So it's the opposite of my log button. So we have negative 5.20. So we get that the pH of 5.20 has a concentration of 6.31 molar. Now this is we're looking for the hydronium ion concentration, so it must have units of molarity on that. The only thing that is dimensionless or unitless is pH. So we now know that since it's a concentration, it's going to have concentration units of molar or moles per liter. We could do the same thing with the next one, 10 raised to the negative 16. and that is going to be 1.000 times 10 to the minus 16 molar. Now pause your video and try the last two on your own with your own calculator. So for our last two, we'll just do 10 raised to each of those pHs. So we'll do 10 to the negative 11.20, and we get 6.310 times 10 to the minus 12 for 4 sig figs on there. And then we have second 10 to the minus 2.42. So now we have 0.00, let's see, 3 sig figs, 380 molar. You could also put that in scientific notation, 3.80 times 10 to the minus 3 molar. So when we're talking about pH, we're talking specifically about the H3O plus concentration, or the hydronium ion concentration. But we can also quantify a value that relates to the hydroxide ion concentration. And we refer to this as the pOH. So again, P referring to the base 10 logarithm, and OH referring to the hydroxide ion itself. So a pOH scale is analogous or similar to the pH scale, and can also be defined as the negative base 10 logarithm of the hydroxide ion concentration. So now we're looking at the hydroxide instead of the hydronium. So we have a very similar equation to use to find pOH. It's the negative log, but now we're using the hydroxide ion concentration, and that gives us the pOH. If we know the pOH and we want to find the hydroxide ion concentration, then we can use the second version of this equation, again very similar to our previous one, where we do 10 raised to the negative pOH. Now some problems give us the hydroxide ion concentration and we want to know the pH instead of the pOH. So we can define a relationship between the pH and the pOH, where the sum of the pH and the pOH are always going to equal 14. So if you know the pOH, you can subtract that value from 14 to get the pH. Okay, you can rearrange this equation, you can get that pH is equal to 14.0 minus the pOH. Or if you know the pOH, or if you want to know the pOH and you're given the pH, you do 14 minus the pH. So you can rearrange that in any way that you need. So let's practice using that. Determine the pOH of a solution at 25 degrees Celsius in which the hydroxide ion concentration is 3.7 times 10 to the minus 5. So we're looking for pOH, and we have the hydroxide ion concentration, so we're going to use this first equation here. So just like we did in our previous examples, we're just going to say that the pOH is equal to the negative log of the concentration given. So 3.7 times 10 to the minus 5 for our A value there. So we just do negative log of 3.7 times 10 to the minus 5. And we get that the pOH is now 4.4. pOH, just like pH, is dimensionless, so it has no units on it. So we set up this problem exactly how we did with pH, except now we know we're using hydroxide ion concentration. So when I plug that in, instead of getting the pH out, I get the pOH out. So now pause your video and try our last two problems here, B and C. we'll set up B and C in the exact same way. So pOH is equal to the negative log of 4.1 times 10 to the minus 7. So we have negative log of 4.1 times 10 to the minus 7. And we get a pOH that is equal to 6.4. And finally, for C, we get the pOH is equal to the negative log of 8.3 times 10 to the minus 2. So we do negative log 8.3 times 10 to the minus 2, which is equal to 1.1 with sig figs and rounding. There we go, 1.1 for our last one there. So as we saw, we can relate the pH and the pOH together. So what we can do is put them onto a scale. So here we have a version of the pH and pOH scale. You'll see that the numbers are kind of opposite of each other, meaning that when we add them up, they're always going to equal 14. So when pH is small, pOH is large, because if I were to add those two columns up, I would get a sum to 14. When pH is large, you're going to get a pOH that's small, because they're inversely related to each other based off of their definition that the sum of the pH and the pOH is equal to 14. So we can see here a bunch of different things that are acidic or basic. So we say that if something has a pH, so I'm looking specifically at the pH column. Here we go, in this column here. If we say that something has a pH less than 7, then it is considered acidic. If something has a pH that is greater than 7, then it is considered basic. The only time that we would have something that is neutral is at exactly 7. So when the pH is equal to exactly 7, that's when we have this to be neutral. Anything above or below that would then be considered acidic or basic. As you get closer to 7, you could say that it's slightly basic or slightly acidic. Like if it's 7.3 or 6.9, something like that, it's slightly basic or slightly acidic, but it is still considered acidic or basic. It would not be considered neutral. You can see some trends in, the samples of things that are considered acidic or basic. So a lot of things that relate to our bodies specifically, like food we eat, things already in our bodies, stuff like that, these are all going to be acidic because gastric juices, the stuff that's in our stomach, is already acidic. So I want to put things in that are going to match that pH so that I don't ruin the pH of my entire body. Okay, so we eat more acidic things. If you have stomach issues, if you have acid reflux and stuff like that, that's why you take a base, something that's something around like milk of magnesia. That's something that helps with acid reflux, because what it does is it neutralizes that acid. If you have too much acid, you need to use a base to balance it out so that you're doing those chemical reactions together. But a lot of stuff that we see out in the world or used to clean and stuff like that, those are all going to be basic. So you have to think about how it relates to our bodies. If it's something that goes into our body, it is acidic. If it's something that can harm our body, such as a household cleaner of some sort, then it's going to be basic. So let's practice relating the pH and the pOH together. So pH is typically what we get when we're in a lab setting, finding out different information about a solution, but we typically find the pH through a pH meter. Therefore, once we know the pH, we can use that information to find the H3O plus concentration, the pOH, and the OH minus concentration. Knowing just one number gives us all three of the other numbers that we could need, because they're all related to each other. They are all related to each other through that logarithmic scale that we just saw on the previous slide. So if we know the pH, we can subtract it from 14 to find the pOH. If we know the pOH, we can find the OH minus concentration. If we know the pH, we can find the H3O plus concentration. So we use all of our equations up here to find that. So what I want you to do is I want you to pause your video and try these two problems on your own, where the first one I give you the pH and I want you to find the H3O plus, OH minus concentration and the pOH, as well as I give you the pOH of bleach and I want you to find H3O plus, OH minus, and pH. Now there's multiple ways that you can go about this using that one number, but no matter which way you take, you're going to get the same number, the same answer, because they're all related to each other. So pause your video and try these two problems independently. So automatically we know pH, that's given, it's 3.3. I personally like to go from pH to pOH. That's just my personal preference, but if you wanted to go from pH to H3O plus concentration, you can do that as well. We're going to use that same number to go from there. So I'm then going to find the pOH next. I'm going to say that the pOH is 14 minus that 3.3. So you get 14 minus 3.3, so we get a pOH of 10.7. Now we can use those pHs and the pOH to find the OH minus and H3O plus. So H3O plus concentration is going to be equal to 10 raised to the negative 3.3. So we could do 10 raised to the negative 3.3. Oops. To get an OH concentration of 5.0 times 10 to the minus 4 molar. Now, to find the OH concentration, you could do one of two things. You can plug in 10 raised to the negative pOH to get the concentration that way, or you can use kW. That 14 that we're using to find the pOH, that's coming from the kW value. Take the negative log of kW and you're going to get 14, and that's how we're relating them. So you could either do the pOH as, the OH minus concentration as 10 raised to the negative pOH, or you can use your kW relationship where you know kW, you know H3O plus, you can find OH minus that way as well. Either way works. Whichever way you're most comfortable and understand it most, please do it that way, because it's not wrong either way. So we could do it, let's see, OH minus is equal to 10 raised to the negative 10.7. 10 raised to the negative 10.7, which gets us, let's just call it 2.0 times 10 to the minus 11 molar. We could also find that by doing 1 times 10 to the minus 14 divided by our H3O plus concentration, just like we did in our previous lesson. And we get the same number, 2 times 10 to the minus 11. So either way that you do that is going to give you the same number, because we're already relating it to kW when we do our pOH concentration or calculation there. Okay, then for our next one, we have pOH is equal to 1.45. You could also, let's see, we could do it this way. Let's find OH minus. We could do it that way. So we do 10 raised to the negative 1.45. So we get, let's see, 3.55 times 10 to the minus 2. We can then use that to find H3O plus. You could do it this way. So we could do 1 times 10 to the minus 14 divided by that answer. We could get, let's see, 2.82 times 10 to the minus 13. Oops, that's a 4. And then we can use that H3O plus concentration to do negative log of that concentration to get our pH that is equal to 12.55. So I went a little bit different this time. In our first example, I did pH to pOH, and then I did pH to H3O plus and pOH to OH minus. In the second one, I did pH to OH minus concentration, then OH minus concentration to H3O plus concentration, and then H3O plus concentration to pH. You could do it that way as well, but you're going to get the same numbers either way that you do it. Now, as we said, our pH and our pOH values are rated on a scale. So they have either a high acidity or a low acidity, high basicity, low basicity. So that scale we can use to consider the strength of an acid or base. So we can talk about the relative strengths of acids and bases based off of that relationship. So as you may recall, back from chapter 9 in General Chemistry 1, when we first encountered acid-base neutralization reactions, we only touched on strong acids, okay? We talked about the difference between a weak acid and a strong acid and a weak base and a strong base, but we really only looked at strong acids and strong bases. That should also be in here. We really only looked at those in terms of the neutralization reactions that we were doing, the stoichiometry that we were using to do those, and we touched lightly on titrations. So the relative strength of an acid or a base is going to depend on the extent at which it ionizes when it dissolves in water, meaning ionizing relating to H+. So how much H+ is created from that reaction itself when it's dissolved in water. So strong acids and bases will fully dissociate or fully ionize in water, meaning that if I have a strong acid, let's say HCl is a strong acid, hydrochloric acid, when it reacts with water, it is going to fully dissociate into H+ and Cl-. However, if I have a weak acid or a weak base, it's only going to partially dissociate. So if I had a weak base, let's just call it HA, okay, it's going to dissociate into H+ and A-. However, it's going to be seen as an equilibrium between those because there's only some of that H+ in the solution and only some of that weak base. So they coexist in that solution. Whereas with a strong acid, it breaks down immediately, it ionizes immediately. We only have H+ and Cl- in that solution, specifically for hydrochloric acid, but whatever the anion is for that. But we always have H+ and the anion in solution. We will never have HCl as a molecule in that solution because it's a strong acid and they fully dissociate, they fully separate in water. So we're going to talk about strong acids today, but we are going to also discuss weak acids in a future lecture. So here we'll talk about strong acids, and our next lecture we'll talk about weak acids, along with strong bases and weak bases. We'll do strong acids and weak bases here, weak acids and weak bases in our next lecture. So we have our strong acids, when they dissociate, they're not treated as equilibria like we just saw with our weak acids and weak bases, okay? We see this process as going to completion. So it dissociates and then the reaction is done. So we have 7 strong acids that you need to memorize. We need to know these strong acids, their names, and their formulas, so that when we see them on a homework or on an exam, we can say, oh, that's a strong acid. It is not an equilibrium. It does not have anything to do with equilibrium. We don't need to do any ice tables or anything like that. It is going from the acid straight into the ions. So we have hydrochloric acid, hydrobromic acid, hydroiodic acid. Then we have nitric acid, chloric acid, perchloric acid, and sulfuric acid. Now we can see our reactions here with water. You can see that they create the H3O plus ion because it's going to be reacting with an acid. These can also all be rewritten without water in them. So as I showed before, we can have HCl that goes to H plus and Cl minus. It shows the same thing because remember that H plus and H3O plus are interchangeable with each other, whether we have water as a reactant or not. So if I don't use water as a reactant, I could just show that it's an acid by it breaking down into H plus rather than H3O plus. That's really just for balancing purposes. So we have all of their reactions here. The only one I want to make a specific note about is sulfuric acid. Sulfuric acid is our only one that has 2 hydrogens, which we talk about more so in a future lecture when we talk about multiple hydrogens in acids. But you need to remember that when it breaks down, only one of those hydrogens is being removed and put onto the water. So we're not getting out SO4 minus, we're getting out HSO4 minus. So just keep that in mind as you're going through memorizing these. All of these break down into H3O plus and the ion except for sulfuric acid, which still has 1 hydrogen on it. Now the thing with strong acids is since the ionization of a strong acid is complete, the concentration of the hydronium ion is equal to the starting concentration of the strong acid. And this comes about through the balanced reaction. Oops. Right? If we look back at our balanced equations, okay, if I know my HCl concentration, then through my mole to mole ratio, I know that 1 mole of HCl has 1 mole of H plus, or H3O plus, remember they're interchangeable, which would then equal the concentration of H plus. So through the balanced chemical reactions, we can say that the concentration of the hydronium ion is equal to the starting concentration of the strong acid based off of that balanced chemical equation. So consider a solution of hydroiodic acid that has a concentration of 0.025 molar. We know that the HI concentration is 0.025 molar, meaning that the H3O plus concentration or the H plus concentration, they're interchangeable, is also equal to 0.025 molar in that same solution. So if we wanted to find the pH, we just do our usual calculation, negative log of that concentration. So we have 0.025 here, we just plug it in there, and we calculate it out to get 1.6. So all we have to do is know that HI has a concentration and H3O plus concentration that's equal to whatever its concentration is. They're equal to each other through this relationship here. And we can use that concentration to find the pH. Now this is only for strong acids. We will not see this with weak acids, which is why that's a different lecture, because we have to do some additional steps because of the equilibrium that weak acids produce. So this only applies to strong acids, which is why you need to memorize your strong acids as well as your strong bases, which we'll see in a second. You need to memorize these so that when you see them on a homework, you can differentiate between what type of problem you have to do. Either a simple pH is equal to the negative log of the concentration type of problem, or if we have to do some additional steps to account for equilibrium. So memorize those 7 strong acids. There's only 7 of them, so not that difficult. So let's practice with this concept. So we want to calculate the pH of a solution that is 3.5 times 10 to the minus 3 molar HBr, hydrobromic acid. And then we want to calculate the concentration of HBr that has a pH of 4.81. So pause your video and solve these 2 problems. Since HBr is one of our strong acids, all we need to do is take that concentration and plug it into our regular equation to solve for pH. So the pH is going to be equal to the negative log of 3.5 times 10 to the minus 3. So you get negative log of 3.5 times 10 to the minus 3. Oops. Times 10 minus 3. There we go. Type it in correctly. And we get out a pH of 2.5. For our next one, we're just using our second equation here. So we want to find the H3O plus concentration, which is equal to the concentration of HBr. They're equal to each other. and that's just going to be 10 raised to the negative pH of 4.81. So 10 raised to the negative 4.81, and we get a concentration out of 1.55 times 10 to the minus 5 molar. We got to keep that molar in there because we're looking for a concentration. Now let's see how this relates to strong bases. So just like strong acids, our strong base dissociations are not treated as equilibria like we would a weak base. Okay? Instead, we are going to see these processes as something that goes to completion. Our strong bases are separated into two different types. We have group 1 hydroxides and group 2 hydroxides. So strong bases are only hydroxides. So as you may remember from your naming unit in General Chemistry 1, there are going to be OHs in there. That's our hydroxide polyatomic ion. Okay, so hydroxide. So we have two different types of hydroxides, group 1 hydroxides and group 2 hydroxides. Group 1 and 2 relating to their periodic table, our alkali earth metals and our alkaline metals, okay? So all of our elements in group 1 are going to form hydroxides, and those are going to be our strong bases in group 1. And then in group 2, we only have 3 of those compounds that are going to be strong bases. Okay, beryllium and magnesium, while they form strong bases themselves, like as a solid, you can have, MgOH2 and stuff like that, and that would technically be considered a strong base. They don't go into solution very well, so they would never be considered as a strong base solution, and if they're a solid, they're not really useful to us. So because they don't dissolve readily in solution, they're not really considered a strong base because they can't be used in solution. So the group 2 strong bases that we need to remember are going to be calcium hydroxide, strontium hydroxide, and barium hydroxide. In your notepad, you are required to write a name for each of these strong bases. So you have to go back to your understanding of naming. We're still going to keep using that naming knowledge from Gen Chem 1. We got to keep that up. So you got to name all of these strong bases for group 1 and group 2 hydroxides. Now when we want to find the pH, the pOH, the OH concentrations for our strong bases, we can follow something similar to our strong acids with one caveat to that. So when we're looking at group 1 hydroxides, we can treat the group 1 hydroxides the same way as our strong acids like we saw earlier, like when we were calculating the pH, because this reaction goes to completion in a 1-to-1 ratio. The only difference that we have to keep in mind is that instead of the concentration of the base telling us the H3O plus concentration or the pH, we have to remember that it tells us the OH concentration or the pOH. So for example, we have a solution of 0.013 molar lithium hydroxide. So our lithium hydroxide concentration is equal to 0.013, meaning that our hydroxide ion concentration is also equal to 0.013. Meaning if we know the OH minus concentration, we know the pOH by just plugging it into negative log of 0.013, and we get out that the pOH is equal to 1.9. We can then do 14 minus 1.9 to find that the pH is equal to 12.1. Okay, so you just have to remember that if it's a strong base, we're looking at hydroxide, so we're looking at hydroxide concentration and pOH. If it's a base, then we're looking at, if it's an acid, we're looking at H3O plus and pH. So just keep those in mind. Now when we move on to group 2 hydroxides, there's something a little bit different that we have to take into account. So since the concentration of a base tells us the OH concentration, when we consider group 2 hydroxides, we have to take stoichiometry into account as well, because when we go into group 2 hydroxides, our relationship is no longer 1-to-1. Okay, it's now 1-to-2. So when we have a solution of 0.013 calcium hydroxide, okay, its concentration, yes, is 0.013 molar, but that does not equal the concentration of the OH minus. Instead, in order to get the proper concentration of the OH minus, we have to take the concentration of CaOH2, calcium hydroxide, and multiply it by 2 to account for balancing. So we have to do 2 times that concentration. Now, if you're someone who thinks in mole-to-mole ratios or just needs math to prove these types of concepts to you, let's say we have 0.013 molar calcium hydroxide. Now, instead of molar capital M, I'm going to write that as moles over liter of calcium hydroxide. Now, using our balanced chemical equation, I know that 1 mole of calcium hydroxide is equal to 2 moles of OH minus. That is just from our balanced chemical equation. This relationship here, where I take that 0.013 and I multiply it by 2, here is directly related to our mole-to-mole ratio. That's why we have to take stoichiometry into account. So whenever we're given the concentration of a strong base that's a group 2 hydroxide, we have to take that concentration and multiply it by 2. So we're going to take 0.013, we're going to multiply that by 2, and we get that that concentration is equal to 0.026 molar. And that's the OH minus concentration. We can then use that to find the pOH. So we'll do negative log of 0.026, and we get that our pOH is equal to 1.6, and then we can do 14 minus 1.6 to get that the pH is equal to 12.4. So we have one extra step that we have to do when we're looking at group 2 hydroxides. So whenever you see an OH parenthesis 2 as a strong base. So let's practice this. We want to calculate the pOH and the pH for the following solutions. So all of these are going to be our strong bases. We don't know what to do with weak bases yet, so don't worry about that just yet. Okay, so we're given all of these concentrations and we want to find the pH and the pOH. So for our first problem here, our pOH is going to be equal to the negative log of 0.0715. I can use that concentration because this is a group 1 hydroxide. So the concentration of the base itself is in a 1-to-1 ratio with the concentration of the OH minus the hydroxide ion. So we can use it as is. So we do negative log of 0.0715. And we get a pOH of 1.14. If we want to find the pH, we're just going to do 14 minus 1.14. And we get 12.86 out as the pH. So now pause your video and try these last 2 problems, making sure to identify if the base is a group 1 or group 2 hydroxide so you can account for stoichiometry appropriately. NaOH is another group 1 hydroxide, so we can use it as is. So we'll do the same thing. pOH is equal to the negative log of that concentration, 1.35. And and we get a pOH of negative 0.130. Yes, you can have a negative pH. It can go up to -1. If you have like a -17, then you just missed your sign somewhere or something's messed up. But you can have a negative pOH and pH up to -1. So just keep that in mind. I know it looks weird, but you are in fact allowed to have a negative pH and pOH. So that's our pOH. If we want to find pH, we're going to do 14 minus a negative 0.130, and we get 14.13. Just like you can have a negative pOH or pH, you can also have a pH that's higher than 14. It can max out at 15. If you look at our pH scale, we saw that. We saw a -1 and a 15 that were together for the pH and pOH. That's the absolute maximum and absolute minimum that pH and pOH can be, because when you add those two together, we get 14. Finally, we have barium hydroxide, which is a group 2 hydroxide. So what we need to do is take the concentration of the barium hydroxide and we need to multiply it by 2 to account for stoichiometry. So we take that 0.094 and multiply it by 2 before we plug it in. So we're going to do 2 times 0.094, and we get out that the concentration of the OH minus is actually equal to 0.188 molar. So for our pOH, we now do negative log of that new concentration, 0.188. So we're accounting for our stoichiometry there. So negative log of 0.188, which gives us a pOH of 0.7272. Now, if we want to find pH, we just do 14 minus 0.72 to get a pH of 13.28. And for our last set of practice for this lesson, we want to determine the hydroxide ion concentration for the following solutions given their pH. So I give you pH and I want to find the OH minus concentration. So the first thing that we're going to want to do is convert pH to pOH. Then once we have the pOH, we're going to do 10 to the negative pOH to find the OH minus concentration. So pause your video and take a second to solve these two problems. So the first thing that we're going to do is do 14 minus that pH. So we do 14 minus 8.15, and we get 5.85 out. And then to find the OH concentration, we're going to do 10 raised to the negative 5.85. So we get 1.41 times 10 to the minus 6, and that is equal to the OH minus concentration. We could do the same thing for the second problem. So we could do 14 minus 9.60 to get a pOH of 4.4. So we do 10 raised to negative 4.4. and we get 3.98 times 10 to the minus 5. Again, these should both have molar on them. There we go. And that is the OH minus concentration. Now the problem here asks specifically for the OH minus concentration. If you came across a problem that asked for the original concentration of the base, since both of these are going to be group 2 hydroxides, we have to take stoichiometry into account. So we can see these molarities as moles over liter of OH minus. So in order to get to our base, we would have to divide by 2 to account for the stoichiometry of the base. So then if we wanted the original concentration, we would divide that value by 2. So look at how the problem is worded. Does it want the OH minus concentration, or does it want the original concentration of the base? Because you're going to have to do some additional steps depending on what they're asking for. If you're asked for the original concentration of the base, then you have to do the second step. If you're only asked to find the OH minus concentration, then you can stop here where we did.